This video shares the correct answers, but also talks about the problem solving for the second kitchen sink free response question that you were assigned. The author is by the name of Melican, so we wanted to honor the labeling of the question with his name. What I'm going to do first is share the question. Please feel free to pause your screen if you need. Then my work and answers. Then talk about the problem solving and also share a scoring guide that I created from just my years of being an AP reader that I hope gives you a feel for what the College Board will probably be looking for. All right, so the question first starts out by being given a reaction diagram, and then the rest of the question asks you to answer parts A through H, I. Okay, so my work and answers. In A, they wanted the overall reaction. I did want to show some work behind it. In B, they're asking which step is the slow step. So I'm going to make sure I answer that right away. And then how I chose to answer. Rate law for C. In D, you had to conclude the sign on the enthalpy for step 1 and step 2. And then justify. In E and F, you had to conclude on the intermolecular forces and then justify difference in boiling points. In G, your KP expression. H, the equilibrium pressure of your HI. And then in part II, you define the number of moles of iodine. Okay, so what I'd like to do now is to talk through the problem-solving approach. So I'm kind of talking out loud while I'm answering the questions to let you know the thinking that comes into my brain as I'm tackling this problem. And then I'll go through the scoring guide that I created. So let me just move out of the way for just a second. Okay, so we want to make sure that we're pausing to really take a look at any data, any graphs, anything that we're first given. And I know we want to jump right into the question. All right, we're given a reaction profile, also known as a reaction diagram. So along here would be time, so beginning and end of the reaction. So what I'm starting with and then ending with. And I'm told it's a two-step mechanism. Oh, so no wonder I had this first hill and then second hill. So this must be, my first set of reactants and the products of the first step and then my second step. Now notice, I'm starting with reactant here and products here at a lower potential energy. So I know overall that will be an exothermic reaction. In fact, this dotted line shows me the potential energy difference. This will be what be released. Now here, the distance from reactant potential energy to the peak of the hill, that's activation energy. Remember, that's the minimal energy that must be inputted to create what we theorize, is an activated complex. This in-between of reactant bonds breaking and product bonds forming. It's a high energy complex, so that is why we need that investment of energy. So this would be the first activation energy and then the second. Okay, let's dig in. So I'm given my steps. So here, reactant, those are my product, then those become the reactant, and then the product. Okay. And remember, a reaction mechanism is made of elementary steps. Excuse me. So we think to take us from reactant all the way to product, first these guys come together and make these, and then so on. All right. First, the overall equation. Well, if this is a possible mechanism, then I should be able to add up the elementary steps, and I should get overall what I'm starting and ending with. Now, a chemical reaction shows what is being chemically changed. So I see HI as a reactant and HI as a product. It's not being transformed, so it gets canceled. Now, the HI is first produced and then consumed in a later elementary step. So I know that we give it the designation of reaction intermediate. Remember that? Where a catalyst is first seen as a reactant and then later as a product. But that's it. I don't have anything else to cancel. So I have one H2, but then I'm going to have two ICLs and then two HCl's and then I2. Okay, there's my answer. Next, identify the slow step. A reaction is only as fast as its slowest step. Okay, how am I going to get that? Well, what determines the speed or the rate? Well, remember, a rate law is K. Now these are my overall reactants. I don't know their orders yet. Okay, so the concentration of them impacts rate, but I'm not told anything about concentration. Well, what else do we know affects rate? Temperature, but I'm not told anything about temperature. Okay, what else? Activation energy. In fact, temperature and activation energy are what factor in decay, as well as collision frequency and correct orientation. But the greater the activation energy, the lower the value of K, the lower the rate. But we don't have to relate activation energy and rate constant. We're okay to just relate the relationship of activation energy to rate. So the greater the activation energy, the lower the rate. And we get activation energy from our reaction diagram. All right. If I'm asked to justify, I'm going to answer the question first. So which is my slow step? Okay, that's going to be the greater activation energy, the higher hill. So that's going to be step one. So my step one is my slow step. Make sure I answer it right off the bat. Okay, how do I know? Well, step one, activation energy, is greater than step two, activation energy. And, I'm just going to go ahead and say, activation energy, that's the height of the potential energy hill. Reactants must overcome to produce product. And the greater the activation energy, the lower the rate. So the higher activation energy of step one will cause the lower rate, which will be then the slow step. All right, when we're justifying, we want the claim, we want the evidence, and we want the reasoning. Okay, then what is the rate law? Now notice, they're saying based on A and B. Don't forget that you are asked certain things in a certain order for a reason. So they're saying, okay, in A, you found out the overall. Okay, in B, you found out your slow step. Well, remember, we only get rate laws from experimental data, but it can be inferred from the reaction mechanism, from the slow step. Remember, we can come up with the rate law based on the balanced equation or the molecularity. The number of each reactant becomes the order. So we're not asked to justify here. We can simply get our rate law from that first elementary step. And so the H2 has an order of 1 and our ICL has an order of 1. Now, quite honestly, you could have made an educated guess if you weren't sure where to go. The majority of reactants in our world are first order, then second, and then 0. So even if you weren't sure where to go, now we want to make sure we're writing a rate law and not an equilibrium expression. We're not asked to justify. That's our answer. All right. D, determine the sign of the enthalpy for your steps. Well, again, from the reaction diagram, it depends on where the reactants compared to the products as far as their total potential energy. When we're ending at a lower, we're going to release that. It will be exothermic. Then the sign on our change of enthalpy is negative. So, first, step 1, negative H. Same for step 2. We want to make sure that we're answering the question. Okay, how do we know this? Per the reaction diagram, if you can't remember what it's called, now of course they call it reaction profile here. You could just say from the given graph, or you could redraw it. So per the reaction diagram, the potential energy of the reactants is greater than the potential energy of the products. Therefore, each step, I would say for both steps, each step releases energy, which then will be translated to be exothermic, which will be a negative delta H. All right. Here's where we transition to talk about how do we explain differences in physical properties. Now, usually whenever we're asked to compare boiling points, the first thing I would suggest is we classify the type of substance. Then, okay, what kind of particle attraction is there? But look, right off the bat, they're saying identify all the IMFs. So they're already establishing for us, they're covalent molecular. All right. So we asked about I2 and ICL. And I sure hope that we can just envision, the Lewis dot structure, definitely nonpolar, so Lund dispersion. And of course our ICL, okay, they're different elements with different electronegativity, so this will be polar, okay, LDF and then dipole-dipole. Now, usually, something like dipole-dipole will have greater particle attraction and then hence the properties that go along with it compared to just Lund dispersion. But here they are saying the boiling point of I2 is greater. So it's all about the Lund dispersion. All right, so we've answered what intermolecular force is. But now, why does this have a higher boiling point? And we know. The greater, okay, but molar mass, we can't leave it at that. The greater the molar mass, the greater the number of electrons. That translates to polarizability. And the more polarizable, the stronger the Lund dispersion force. So, I2 number of electrons is greater than ICl number of electrons. Therefore, I2 more polarizable, I2 LDF strength greater than the ICl LDF strength. Therefore, I2 requires greater energy investment to boil, equals a higher boiling point versus ICl. All right, now on to F. Okay, now part F is asking us about HI and HCl. Okay, both of these are polar. Lund dispersion, dipole-dipole. They do not meet the requirements for hydrogen bonding. Remember, that is hydrogen directly bound to either fluorine or oxygen or nitrogen. Nope. Okay, so they're tied, if you will. Now, we want to look at, okay, which one has the greater boiling point, and it's HI. Now, can I tell you that I'm glad they tell us about that exception, because I would naturally conclude that HCl would have a greater boiling point, because we know as we get closer to fluorine, the electronegativity increases. And so we would say that, you know, the electron density is spending much more time around the chlorine versus hydrogen than iodine versus hydrogen. And so we would say that the dipole-dipole force in the HCl is going to be stronger than the dipole-dipole in the HI. But HI has the higher boiling point. So it must be those LDFs again. And you would go with this same, explanation. That the greater the molar mass is the greater the number of electrons, is more polarizable. These are all just the perfect terms. So we want to make sure we're hitting them. Is stronger LDF. Your HI number of electrons is greater than the HCl number of electrons. Therefore, the strength of the Lund dispersion in HI is greater than the strength of Lund dispersion in HCl. Now, I've already said more polarizable, but I'm going to go ahead and say just here. AP readers love that, more polarizable. Those electrons, there's just more that will be found in one area versus another, so making that temporary negative a little stronger. Therefore, the boiling point of HI is greater than the boiling point of HCl, requires more heat to boil. All right. Phew. Almost home. All right. Now change things up a little bit and get to a little bit of equilibria. So now we're given a reaction where we have all gases. Okay, and we're given the temperature and the K value that corresponds, Kp, and they're asking us first to write the Kp. Okay, so we know we have to be careful and reference partial pressure of product and applying the law of mass action over partial pressure of reactant. I don't have to write that it's equal to 50, but it just takes a second. All right, now HI. Okay, a rigid 1 liter vessel, so the volume is not easily changed. Initially, okay, I'm thinking an ice table has pressures of 1 atmosphere of hydrogen and your I2. Find the final pressure of HI. All right, yeehaw, get to do a little ice table. All right, so we initially have 1. Oh, that is just terrible sig figs. I'm going to take the liberty of going ahead and attaching 1.0. I know I'm going to have to do some calculations. They're not saying be careful of your significant figures. I think that this was an oversight, really. It's very rare that we'll just get one sig fig. And we're not starting with any of the product. So we know that we are going to be shifting right. Be careful. It'll be minus 1x for both reactant, but then plus 2x for the HI. Okay, so we are going to have to plug these expressions into our KP. And so it will be 2x squared over, oh, look at that. We can combine these to square those. And then why don't we take the square root of both sides? Nice. And then, let me just quickly find my work, ladies and gentlemen. That will be 7.1, and that will be then 2x over the 1 atmosphere minus x. Multiply that by both sides. This is a combined, of course, expression. So that would be 7.1 ATM minus 7.1x equals 2x. Move everything around, and we end up getting x is equal to 0.78 atmospheres. This is asking for the pressure of your HI at equilibria, which is 2x. And so multiplying that by 2, we get 1.56 atmospheres as the answer for part I. All right, last part. Now they're asking for the moles of I2 that remain after the reaction has come to equilibria. Okay, well, what do I know about the I2? Well, I know the pressure that it'll have when it gets to equilibria. So the pressure of the I2 will be the 1 atmosphere minus the 0.78. So that's going to be 0.2. Oh, and I know it's a 1 liter vessel. We were told that. And I also know the temperature. So PV equals nRT. Can I get moles? I know the pressure, the volume, and the temperature. We know with the ideal gas law that we have to take a lot of care with our units. Our pressure has to be in atmospheres, which it is. Our volume has to be in liters, which it is. The R value is given on your equation sheet. And we need our temp to be in Kelvin. I reported to the 10 place just to go ahead and respect the sig figs of that 450 Celsius. So it's 720 Kelvin. And then limited to 1 sig fig, 0.003 moles of I2. Okay, I went ahead and created a study guide attributing 15 total points to all parts. So you would have earned 1 point for the correct equation for A. For B, 1 point for designating the correct step to be slow. And then 1 point that the justification relates activation energy to the rate. C, 1 point for the correct rate law. D, 1 point getting both enthalpies to be negative. And then 1 point justifying that by talking about the potential energy difference of reactant to product. Part D, 1 point for the correct intermolecular forces. And then 1 point that the justification compares Lund dispersion and polarizability. So then F, 1 point for the correct intermolecular forces. 1 point that the boiling point difference comes because of differences of polarizability and the strength of Lund dispersion. G, 1 point for correct KP. For H, 1 point that the relationship of the coefficients or the mole ratio of your species came through properly. So that is shown in the C line of your ice table, but also could be revealed in the solving of the KP expression. And then 1 point for getting the right answer, 1.56 ATM. Okay, and then 1 point for realizing that you can get the pressure of the eye too by working from what you just had found with your ice work. And so you take your initial pressure minus the amount that would have been lost, and then applying the ideal gas law. So 1 point for that, but then 1 point for applying the ideal gas law correctly. That is a total of 15 points. We want to be securing, hopefully, about 12 out of the 15 points. Hopefully, if similar questions come your way, you will just keep getting them correct, or you'll improve upon your mistakes to get them correct next time. Best of luck.